Okay, so in this problem we have a spool of mass capital M, which has a radius of gyration about its center of k0, and we're told that this spool rolls without slipping on a rough horizontal surface. We're furthermore told that a cable is wrapped around the inner radius of the spool, and that this cable is pulled over an ideal pulley and attached to block A. We're asked to assume that the cable does not slip on the drum, and that the system is released from rest in the configuration shown. Given this information, we're asked to determine the angular velocity of the spool after 10 seconds. Okay, so the way I would go ahead and do this is a little counter to what we normally do. Typically speaking, when we want to find, in this case, an angular velocity after a given period of time, I suggest that we use purely angular momentum methods and try to make the system as large as possible. If you do that in this problem, it can be a little prohibitive, and it has to do with the very simple fact that, as I often tell my students, you can't sum and apply Newton's second law around corners, if life was only so easy. So instead I'm going to draw free body diagrams separately here for the spool and for the block, and I'm going to apply separately, in this case, linear impulse momentum methods as well as angular impulse momentum methods to ultimately get my answer. So if I draw the free body diagram of the block to start, we know we'll have some tension force acting up, and we'll have the weight of the block m times g acting down. If I then come across and look at the spool, I know I'm going to have here the tension force T. I'll have some normal force from the contact with the ground, as well as some friction, which is going to prevent that from slipping, and we'll have the mass of the spool here, which I'll call m times g. So the key thing I'm going to do now is I'm going to apply linear impulse momentum methods and angular impulse momentum methods to see if I can find the angular velocity of the spool after the given interval of time. So I'm going to go ahead and define my x and y coordinates as I often do, and I'm going to apply linear impulse momentum equation to the block in the y direction. So if I do this, we know that the block is initially not moving in the y. I'm then going to have a net impulse on this, which is the integral of t minus mg times dt, and that's going to equal the final momentum in the y direction, which I'm going to write as being minus m times what I'll call v2. And I'm going to put the minus sign here to account for the fact we're going down, and v2 of this will be downwards positive. So if I do this, I can go ahead and assume that the average force is active over the interval, so I'm going to have here t minus mg times the amount of time elapsed, delta t, is going to equal minus m times v2. And let's go ahead and call that equation 1. Now that I have that equation in hand, I'm also going to apply the linear impulse momentum equation on the x direction, and in this case I'm going to do it, of course, on the spool. So if I have this initially the object's at rest, I'm going to add to this the net impulse in the x direction, which is going to be t minus the friction force. Multiply that by this will be still dt because we're taking the integral. And that's going to equal the mass of the spool times the speed at point O at state 2. And we can call this equation 2. And actually, I'm not going to call that equation 2. I want to expand the integral just like I did above. So I'm actually going to write quantity t minus f times delta t is equal to m times VO2 as equation 2. Once I have that in hand, I can also now apply the angular impulse momentum equation. I'm going to do so in a counterclockwise positive sense. I'll do this to the spool. So in this case, I know again the spool is initially at rest. I'm going to have a moment arm created by the t force, so I'm going to have the integral of minus t times its moment arm, which is what we call little r in the problem statement. Then I'm going to also have a negative moment contributed by f, and its moment arm is going to be big R, will be dt. That's going to equal I about O, which for the spool is going to be the mass, which is capital M, times k0 squared, times what we'll call omega 2. Again, I can expand the integral here, and so I can rewrite this as t times r times delta t minus f times r times delta t is equal to m times k0 times omega 2, and we can call this equation 3. Now if we look at equations 1 through 3, we currently have 1, 2, 3, 4, 5 unknowns, and we only have, in this case, let's count them here, 3 equations. So I'm going to need to use some kinematics here to help myself out. And these kinematics aren't going to be too difficult. Namely, I'm going to use the fact that the point in contact with the ground on the disk is an instant center. And so what I can say here is, because of that, VO2 is going to equal minus big R times omega 2. The minus here comes from the fact that VO2 is defined to be positive to the right, and omega 2 is positive counterclockwise. And if I use somewhat similar logic, I can say that V2 then is going to equal minus quantity R plus R times omega 2. Let's call this equation 4 and equation 5. If we now look, we've added 2 additional equations without adding any additional unknowns. So we have 5 equations, 5 unknowns, one of which is omega 2, the angular velocity you're asked to solve for in this problem. So from here on out, this is a relatively straightforward exercise in substitution, and one I know you have well under control. So I'll simply bid you an adieu, and best of luck.